So today, what I want to do is I answer some homework questions. If you guys don't have homework questions, I have some things I want to talk about in homework. And then I want to talk about 11.5, and then one idea from 11.6 to sort of motivate where the class goes from here. Right? So 11.5 and one idea for 11.6, just to kind of tie everything together so far. And then that's it. So what's on my agenda today? If we have time at the end, I'm going to give you another pile of questions, but I don't anticipate that being necessarily something that's going to happen. And then remember that tomorrow there's a quiz, but it's not a graded quiz. We're going to go through the motions of doing a quiz. I'm going to hand it out. You guys are going to have 10 or 15 minutes to work on it. Then we'll talk about how the quiz questions, like exactly what the answers to the quiz questions are. And then you can file that away into things I'm likely to pull out again when I'm thinking about how to construct the exam. Yep. I am going to post the PDF file of the quiz prior to the session. So I'm going to write it, I'm going to put it up online, and like I'm trusting that everybody online can just download it, look at it on their screen, and work on paper in the same period of time. Okay. So yeah, if you can't be here tomorrow, or you don't plan to be here tomorrow, my intention is to provide the quiz simultaneously on the Canvas page, so that you can walk through it either asynchronously, or you can walk through it like along with the recording, or you can walk through it synchronously with the rest of the class. All right, so yeah, so I'll say sort of a quiz. For tomorrow. I can call tomorrow. So, any questions about anything non-homework related I can answer before we get started? Yep. I'm going to do 11.1 and 11.2 in a separate, I'm going to record a separate video where it's sort of like a fake class where I'm going to give out the quiz. I'm going to have to, I give you a fake time, like 10 or 15 minutes. So it'll be 10 minutes of dead space where I'll just sit and look at the camera. And then after that, I'll go through the answers to the questions. It's just to give you a recreation of what, you don't have to watch a video where I just like do nothing for 10 minutes and then explain the answers, but it's at least a recreation of what it would be like to take in a class. So that'd be separate from 11.3 and 11.4. So I'm going to go back and reconstruct 11.1 and 11.2. Nails? All right, homework questions. Number 11, which was?
Sum from minus 33 over n factorial.
Sum from n equals 1 to infinity.
33 over n factorial.
33 over n factorial?
Yeah.
What section was this from? 11.4. Okay. So here's kind of an awesome thing about factorials, right, on the comparison test. You can use them. Actually, what is the language around number 11? That's a good question. What does the rest of the question say? Because I'm actually looking right now in the comparison test section here. Now, of course, the hard part about factorials is that you don't know an obvious comparison, right? So do the languages say determine whether it converges or diverges? Okay.
I think so, yeah.
So let's just engage with it the way that it is on the page here. What should you suspect? This is the first thing I want you to think of is what should you suspect this does? And so again, when you're looking at your suspicions, I want you to think about what the orders of growth for various things are, right? The faster something goes to 0, the faster its series converges. So what I think in terms of orders of growth, so what I'm going to give you first is I'm going to give you an answer that is sort of the intuitive answer that you might get if you didn't know what to do and you were looking at this thing on an exam, but you had no idea where to go with it, right? So the orders of growth were that you had logarithms, and those were slower than polynomials. And in particular, I'm gonna split the difference between polynomials that have n to the p where p is less than 1. And then we had polynomials So then greater than that are polynomials n to the p, where p is bigger than 1. And the reason that I'm doing this is because I'm trying to split the difference between things that diverge and things that converge, right? And those were less than anything that looked like an exponential. The things that look like r to the n, where r is bigger than 1. And those were smaller than things that look like factorials. So the big dividing line between the way things go to infinity, what I mean here is how fast do these things grow to infinity? And there's a split right here where everything on this side, when you turn it upside down, makes a divergent series. And everything on this side of the line, when you turn it upside down, makes a convergent series, because this p equals 1 line of the polynomials, that splits things that converge from things that don't. So your general sense here should be, well, I'm looking at 1 over a factorial. And factorials are like the fastest growing thing we deal with. So 1 over something that's going to infinity really fast is going to 0 really fast. So your suspicion should be, this should converge. And in fact, it should converge very quickly. This should converge. In fact, some of you actually might know what this converges to. Does anybody actually know off the top of their head what number that is? It's 33e. One of the things we're going to learn in power series is that one of the ways to express e is the sum of the factorials. Sum of the reciprocal factorials adds up to e. So it should converge. So the easiest way to explain why it converges, in the book, now they bury this down in a homework exercise, which is it's kind of ridiculous, because the result that you want here says, so there's this souped up version. There's a souped up version of the comparison test that allows limits at 0. So remember, when we wrote the comparison test down, we wanted the c to be strictly between 0 and infinity, right? But I'm going to give you a version that works when one of the series is completely dominated by the thing you're comparing it to. So what it says is this. So suppose that an and bn are power series. And this is a convergent sum. To prove the limit as n goes to infinity of an over bn is equal to 0. So you have terms that are dominating, like, let's see what's actually happening here. These are both running away to 0, but this is going to 0 faster than that's going to 0. Okay. Then an is also convergent. So what this lets you do is it lets you consider sequences that don't actually have the same behavior. What this is saying is these terms are going to 0. So, I mean, if this series converges, then these terms are headed to 0, right? For this limit to be 0, but for this to be 0 over 0, for this limit to be 0, this actually has to be going faster than this to pull this whole thing to 0. I don't know if that makes sense or not. Okay. But this is one approach you can take to a problem like this where you don't actually know what to compare this to. Okay. Now, I don't actually know what the hell is book. This is what I would use to think about this.
There was a video like along with it, but I did not understand what.
A video. I mean, I don't even see the n factorial problem in here.
Just ask to determine whether or not it's convergence or divergence.
I mean, that's all it said. Okay. No, but I mean, in the video, what did they say in the video?
They compared it to some really, like, to another function, but I didn't understand why.
Okay.
So
I'm just curious now because I think those videos are sometimes suspect. I don't know if you guys watch them, but sometimes they're enlightening and sometimes they're completely unenlightening. You don't need to pull the video out and look at it. But I mean, as a comparison here, all you need to be able to say is that 1 over n factorial is less than some other terms where this converges. So forget this, which was done in the homework exercise, like way after all the rest of the stuff. Just think about this. 1 over n factorial less than an. Well, so one thing that is true is that really what that means is that you want to know when n factorial is larger than something. Where when you take the reciprocals, you know that this side converges. In particular, one useful comparison is that n factorial is bigger than 2 to the n. Eventually, right? Because multiplying a pile of 2's together is going to be smaller than multiplying an increasing pile of numbers together, right? 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. 2 to the 6th is 2 times 2 times 2 times 2 times 2, which is smaller than that. So eventually n factorial is bigger than any exponential. And that means that 1 over n factorial is less than 1 over 2 to the n.
Think of these in the
I mean, you could pick anything here that you know converges when you flip it, right? But the idea is because you know that factorials are bigger than exponentials, you can cheat. When I turn this over, does that series converge? This series. Why does that converge? I'll give you a hint. You can rewrite it as 1/2 times 1/2 to the n minus 1. Geometric series, right? Every time you get the next term by multiplying by 1/2. If you just even wrote the terms of this out, you're going to get 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. That's a geometric series because each time you're multiplying by 1/2. So this series converges. So since this series converges, and this has to be smaller than that because factorials are bigger than any exponential, then this must also converge. So your inequality doesn't have to be good. It just has to exist. You have to be able to compare something that you know converges to something that you're testing. And the way that you would be led to this comparison is by knowing that factorials are larger than exponentials. Does that make sense? I mean, you could have put any number in here. You want 10 to the n, that's going to work, right? As long as the number you choose here is going to infinity, this will always be true. Okay? So yeah, I mean, this is why this is hard, because this is, a mathematician would call this ad hoc. It's an ad hoc estimate. There's no method that would lead you to this. It's the observation that factorials are bigger than exponentials. So there's some creativity involved in choosing the right comparison. But even if you didn't have this specific thing, you could still answer the question by saying that thing has a factorial on bottom, which is smaller than exponential, which is smaller than a p series. This, in fact, you could put a p series over here. I mean, that's also true, right? Factorials are way bigger than squares. But this also converges when you flip the reciprocals. So as long as you put anything on this side that you know how its behavior, what its behavior is, the comparison test is going to work. That make sense? Okay. And so this is what I mean, like, it's not that the videos are wrong, it's they're not necessarily telling you why they're choosing the things they're choosing. They're just asserting that these inequalities hold because they have limited time. Anything else? It's a really good question. Yep.
I have a question about the 11.3 homework.
Please.
Number 4.
Which was?
The sum of from n equals 1 to infinity. The fraction on the top square root n plus 6. That's square root n.
Oh.
6.
Right.
On the bottom n squared, and this is this is the sum of two P series, find the P.
This is the sum of two P series, find the P.
Yes.
Well, I mean, one way to think about this. So first off, why should you believe this converges? You can't start breaking stuff up unless you know it converges. That's the first rule, right? Why does this converge? Without splitting it. I believe that is a convergent piece, like this converges because I think it behaves independently like a P series. Which P series does it look like? I got multiple questions about this in Slack, by the way.
1 over 3 halves, or into the 3 halves.
How'd you get that?
When you go to infinity, the 6 goes away. and-
Yeah. Okay, so that's what you should believe is happening in this series, right? That this thing is actually on the order of a P series, P to the 3 halves, right? Now it's not a P series of that because it doesn't look like a P series, but you could actually split it. Now, at this point, this estimate should make you believe it converges. And that's what justifies doing the pulling apart that we're going to do now to show what the two P series are. Okay, so it converges. In fact, you can show that it converges by the limit comparison test with 1 over n to the 3 halves. That would be the easiest way to do it. Take this, divide it by that, and compute the limit. What you're going to end up is this will flip to the top, and it's going to turn this into an n squared. And then this limit should be 1. Okay. Now, if you want to compute P series for the two pieces that make it up, well, because the series converges, because we have convergence, I'm allowed to use things like, you got to be really careful when you're dealing with series with using the ideas of mathematics that you're used to. So if I just give you that and said, can you break that fraction up into two pieces? You'd say, yeah, you can take the fraction and break it up. What you want to do here, if this was a finite sum, what you want to say here if you were breaking this up is you want to say, oh, well, I can just split the fraction apart. That's only justified because you had convergence in the original series. So this is probably not that I actually asked for you as part of the homework exercise, but if it did, the fact that I broke the series up is only because this limit existed. And even then you have to be careful. Okay. So you got this, and this is just sum from n equals 1 to infinity of 1 over n to the 3 halves. Plus 6 times the sum from n equals 1 to infinity 1 over n squared. So if the question was what are the p values, it's 3 halves and 2. Okay, but I wouldn't, I mean, as a mathematician, I wouldn't think about this as two P series. I would think about it as a series that acts on that order. Okay. Anything else? All right, so I actually have one extension question to ask you guys. What do you think if you want to ask another homework exercise? So somebody comes up to you and gives you this series. So this is related to this idea. Wow, it's nasty. Square roots all over the place, right? What is the behavior of this series? What should you believe about it? What does it do? Converge or diverge? Why?
Well, because you get like a 3.5 n minus, like, you know, half n.
Yeah, so when you're looking at something like this, one of the things that happened that I got questions about in the videos about these exercises was you would get an expression that would say like this one, and then the video would just say, oh, just ignore the 6. Deal with it without the 6. And I'm not sure if it actually goes through the process of saying what you're really doing is you're saying at for large values of n, the only thing that matters are the leading terms, right? The same argument also applies for things inside of a square root. It's still the case that when n is large, what's inside this square root starts to look like n, and what's inside this square root starts to look like n to the fifth. So as n goes to infinity, and yes, this is an appropriate way to attack this question if you were looking at it on an exam. To show me what your thinking is for getting the comparison, it's okay just to do asymptotic analysis. What happens when n gets big? Well, the top of this starts to look like root n, and the bottom starts to look like root n to the fifth. And then you just have to remember how that works. So that this thing basically looks like 1 over n squared. 5 halves minus 1 half is 4 halves, which is 2. So this should converge. This part of the process is a huge part of solving this question. So if you're sitting on something on a quiz or an exam, and you don't actually know how to apply the test, but you do this, you've already done most of the work because you did the analysis that shows me you understand why it converges, even if you didn't claim the formal test to do it. Okay. So the way you would do this is by what? What test would you use here, by the way? There's only one possibility for how you would attack this question if you actually wanted to use one of the convergence tests on it. I would not, let me point one thing out. I would not want to try to untangle the inequality of this is less than or equal to that, because there's going to be a whole lot of crappy algebra involved in making sure that happens. Quadratic inequalities, terrible. You should use limit comparison on this question. If somebody gave this to you to do, you would use the limit comparison test on it. Okay. Part of knowing what's going on a given series is not just identifying what you think the series is doing, but coming up with a method that will tell you. I'll point out that one of the things we're going to learn is a way where you see a factorial in a question, that you automatically always do the same thing with factorial. It's called the ratio test. That's 2 chapters ahead in the future. But the idea is, if you can get a comparison, but you've got something that you don't want to do algebra on, use the limit comparison test. Unless you really want to find the value of n for which this is less than this. I don't really want to do that. I don't even know if it's true for all n. Because I don't know what the balance is between the 6 and this power down here. Don't do this. This would be required if you wanted to use the comparison test. So if you're using a comparison test and you write something like this down and say, oh my God, no, just use the limit comparison test. Okay. All right. Anything else on integral tests or comparison tests before we go on to alternating series? All right, let's do it. All right. This is 11.5 alternating series test. And this is meant to at least partially answer the question, what happens when the terms aren't positive? What happens? Have a series, AN. The ANs aren't all positive. And the answer is, it's a total nightmare. Unless they alternate, then it's easy. So you can imagine you can have a series that has 3 positive terms, then 4 negative terms, then 2 positive terms, and then 6 negative terms. Does that add up to anything? And that's really tricky. Unless terms alternate in sign. Plus, minus, plus, minus, plus, minus, and so on. Then there's a very easy test check for it. All right. So, there's a definition. An alternating series has terms that alternate the shock between positive and negative. The prototypical example for this, these tend to take forms where there's something that looks like -1 to the nth power of the terms. Because -1 to the first is -1, -1 to the second is +1, -1 to the third is -1, -1 to the fourth is +1, and so on, right? So powers of -1 flip back and forth. And so every alternating series can be written with a power of -1 floating around in the formula. Okay? So -1, 1, -1, 1, 1, 1. And we way back when we defined series, we noted that this is divergent. And it's divergent because the sequence of partial sums never settles down on anything, right? If you look at the sequence of partial sums here, S1 is -1, S2 is 0, S3 is -1, S4 is 0, and so on, right? The sequence of partial sums never settles down, so it has no limit. So that is a divergent sequence. Series, I should say. Makes a divergent series. But this guy which is -1/1, +1/2, -1/3, +1/4, -1/5, and so on. This series actually turns out to converge. This has a limit. Numerically, you can check that this has a limit. So if you continue adding terms to these partial sums, they turn out to converge to something. Now, this is just an assertion at this point. I haven't told you why it converges. I'm just saying it does. What's the difference between this series? What's the difference between this series and that one?
The divergent one cancels out its progress.
The divergent one, what?
Cancels out its progress.
It does, but there's actually an even easier way to say that. What does the test for divergence say about this series? Test for divergence says that what has to happen in order for a series to even have a chance of converging? The ANs, not just that ANs decrease, more than that. They have to go to 0, right? If a series has a prayer of converging, the terms have to go to 0. The limit of this is not of these guys. If you wrote down -1 to the n, the limit of that is not 0. It doesn't have a limit, right? That has no limit. So the test for divergence tells you this is divergent. Here, even though this looks like a p series with p equals 1, so if this was positive, it's divergent, right? Sum of 1/n is a harmonic series and divergent. I put the -1 in here and suddenly it's a convergent series. Maybe, with alternating series, tending to 0 is enough. It wasn't enough for positive terms, but maybe for alternating terms, it is enough that if it alternates and the terms go to 0, then the series adds up to something. This is the first big difference between series with positive terms and series with alternating terms. So the sum from n equals 1 to infinity of 1/n diverges because it's a p series. The p series are only positive term series. They have to have positive terms. On the other hand, if I take that same series and I make it alternate, now at least numerically, it looks like it converges. Converges. So in some sense, it's actually easier for things to converge when they alternate. I guess the idea, the intuition is, if you're adding and then subtracting and then adding and then subtracting, as long as that's tending to 0, that you're clustering around some number because you're above it and then below it and then above it and below it and above it and below it. So what the alternating series test says is that if you have an alternating series, as long as the terms go to 0 in the limit, that's enough for it to converge. That's not true in the positive case. So you have to make sure that you can separate all of the previous tests that we've done, which apply to series with positive terms, from these. Okay. What the alternating series test says is, that's the limit comparison test. Wrong section. It says, if you have a sum specifically of the form where there's that -1 to the n in it, maybe I probably write it as n minus 1. So you have an alternating series, which is b1 minus b2 plus b3 minus b4. And so somebody said decreasing. That is one of the conditions. Bn plus 1 is less than or equal to Bn for all n. So the series has to, the sequence has to decrease. The positive numbers here have to decrease. And the limit as n goes to infinity of Bn is 0. So decreasing with a limit of 0. Then series converges. Okay. So how would you use the alternating series test? Here's how it goes. Let's think about that series for a second. So somebody comes along and writes down -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6. Says, does it converge? And immediately you think, okay, I can't use the geometric series test on this because it's not geometric. I can't use the integral test because that requires positive terms. I can't use the comparison test because those require positive terms. So if I want to test this alternating series, the only test I have is this one. So if I took the alternating part out of this, the non-alternating part is Bn equals 1 over n. It's 1 over n, right? It's 1 over n, but flipping signs back and forth. Make sense? When you're looking at the alternating series test, these are checked after you take the alternation out. So this is the non-alternating part. Is it the case? Is it the case? We'll test it now. Now time the boards aren't straining to see. So 1. Is Bn less than or equal to Bn plus 1? This requires algebra. You have to show the sequence is decreasing. I've got it backwards. So you write down the formula. Bn plus 1 is equal to 1 over n plus 1. Bn is equal to 1 over n. Is it the case that 1 over n plus 1 is less than or equal to 1 over n? Sure, right? Bigger number makes smaller fraction. Check. Condition 1 of the alternating series test is true. 2 is the limit as n goes to infinity of Bn, which is the limit as n goes to infinity of 1 over n equal to 0? Yes. the limit of this is 0 as n goes to infinity. Check. Therefore, the sum of -1 to the n times 1 over n converges by usually AST for alternating series test. To use the alternating series test means to check both conditions. Now, where does this go wrong? Frequently, what students like to do is look at an alternating series test, look alternating series and say, it alternates, therefore it converges. Just ignore this part and say, well, it's obvious that if you wrote it down in the exam and it alternates, it must converge by the alternating series test. Which is true, but you still have to go through the motions of checking the mathematics. Or, this is even funnier, if people don't check the fact that it's a decreasing sequence, right? If you can't be bothered to do the algebra, or you just write this down without doing any sort of algebra at all and say, yeah, sure, it converges, right? It's obviously true. I mean, this one's easy. There's examples of harder series. But just like with the integral test, where you have to check 3 conditions to justify the test, the alternating series test requires that you check both of these conditions or you can trick yourself. So I'm going to do a couple examples of alternating series, but I think this is actually a natural place to fold in an idea. From 11.6, which is the relationship between positive series and alternating series. Okay, so I'm gonna sneak in an idea from 11.6. So this won't be on the homework, but I think it's important to put it in here. So the idea is that some series are more convergent than other series. So this guy converges by the alternating series test. But this guy diverges. Well, it's kind of crappy convergence, right? If the terms aren't going to 0 fast enough to make the positive elements add up, but somehow I cheat by flipping them with negative signs and they do add up. So the same series, if I subtract it, converges, but if I don't subtract, put the alternating subtractions in, it diverges. I want you to compare that to the case of this. Well, this thing converges. The P series would be equal to 2, right? This is convergent. And also, this is convergent. I mean, obviously, 1 over n squared is going to satisfy the same properties, right? This is a decreasing sequence. Its limit is 0. This converges by the AST. Alternating series test. So here I have to alternate to get convergence. Here, even the just terms all by themselves before I add and subtract also converges. So it turns out to be the case that you can sort series into different types of convergence by what the relationship is between the alternating terms and the absolute value or the positive terms. It turns out to be a theorem that we'll see next time that every series that has the property that converges when the terms are positive will also converge when the terms alternate. This type of convergence implies this type. This is called absolute convergence. It's convergence of the positive terms all by themselves. That means these are going to 0 pretty quick. Absolute convergence implies alternating convergence. But alternating convergence does not imply absolute convergence. Just because it adds up when they alternate does not mean it adds up when you take the positive parts or the absolute values. Alternating convergence does not imply absolute convergence. We use absolute here for absolute value or positive, right? Okay, what that means is This type of convergence in some sense is stronger than this type. Everything that does this also does that. But everything that alternates, that converges under alternation does not converge in the absolute value. In fact, this difference in these situations is so bad, it leads to one of my favorite bizarre things that people think mathematicians just made up. We have nothing better to do than sit in our offices and say weird stuff. It turns out to be the case. All kinds of things are true about series that converge this way that are not true about series that converge this way. So, for example, do you think that some numbers, is that true? What's that called, by the way? Not commutative means that you can flip the order of multiplication or of addition. It's called the associative property. I can group adding up however I want, right? And you probably also believe that now you say commutative property, that I can do this if I wanted to and get the same answer, right? In fact, I can rearrange a finite list of numbers any way I want, and it's still going to add up to the same number. At the end of the day, this is always going to be 10, no matter how I do it, right? Okay. So this thing always adds up to pi squared over 6, no matter what you do with it. It always adds up to pi squared over 6. Always. And I don't know what this adds up to, but even if you make it alternate, that always adds up to the same number, no matter how you rearrange it. Any rearrangement of this always adds up to the same number, same way we did here. Any rearrangement of the alternate version of it also does. And one of the profound betrayals of arithmetic, though, it turns out to be the case that if you wrote this down, this equals any number you want depending on how you arrange the terms. And that feels like ridiculous. That's a violation of the idea here that I should be able to do addition in any order I want and get the same answer. These things that are in this category, things that converge when they alternate, but not when you take their absolute values, these are not nice things. Because I'm telling you, if I did the same thing where I took this list and I say I put 1,000,000 positive terms first, and then I did the rest of the series, it would add up to a different number than if I compute it this way. If I compute this series by rearranging the terms, it changes the answer. Yeah, there should be confused looks about this one. This does not satisfy the commutative property. The limit of this thing, when you compute the partial sums, will be different if you rearrange the list. That means all series that are alternate but don't converge when you take their absolute values are delicious mathematically and horrendous for physical applications. You have to be careful. And this type of condition of convergence is so sketchy that has a special name. Anybody know the name of this, by the way? I heard somebody whispering. This is called conditional convergence. So it's very easy to check the convergence of an alternating series, but the thing you get out the other side, I mean, how useful is it if I can rearrange the numbers and get different answers? Right. So these are mathematical oddities. Now, conditional convergence is was talked about in chapter 6, 11.6, but I feel like it's important to introduce here because you get the idea that alternating series are great because it's so easy to check if they converge. It's just the problem of what you get out the other side is something that you got to be careful actually using the thing. This not satisfying commutative properties, like, why would anybody ever work with that? All right, so let me do one example, kind of a gnarlier looking, what does an alternating series look like in practice? And then we'll pull it up. Okay, so how about we look at, I mean, this is too easy. It's too easy. Oh, okay. Here's a tricksy one. -1 to the n times 3n plus 1 over 2n plus 2. You can eyeball that and tell me what's going on. Okay, it doesn't alternate. Yes, it does. Boom, -1 to the n inside of it. Great, it's an alternating series. What do you notice about the limit as n goes to infinity here? What does it do? Divergence series. Just because it alternates does not mean it converges. These still have to go to 0. Okay. This limit is not 0. So the alternating series test does not apply. In fact, you would say this diverges by the test for divergence. This limit is not 0. All right. Then there's these guys like these dudes. Okay, here's a math professor's favorite way to make a hard question, an easy question into a hard question. Now, there you are in your exam, and you're sitting there looking at that thing. The first thing you should observe about this is that, well, for different values of n, this thing doesn't have to be positive, right? N was equal to 3. Oh, okay. Are you required to know your basic cosine and sine of basic values? Yes, you should know. What's the cosine of 3n? All right, sorry, 5. -1. It's cosine of 4 pi. Positive 1. Oh, it's an alternating series that my bastard professor hid inside of a question that looks like it's got a cosine in it. So to do this with the alternating series test is dead easy, but you have to realize, probably right by writing terms out, right? If you don't see what's happening, write terms out. If you wrote some terms of this, when n equals 1, you get cosine of pi over n, which is -1 over 1. N equals 2 makes cosine of 2 pi, which is 1 over 2. Oh, okay, you realize, oh, look, it's just an alternating series where in order to make it complicated, somebody put a cosine in here. Okay, so that this series is really secretly the series -1 to the n over n, and that one will converge very easily by the alternating series test, okay? And you know math professors love problems like that. And since I am a math professor, by the transitive property of hard questions. Anyway, so watch out for that in the homework in particular. There will be some probably that want you to translate problems that don't look like they alternate into problems that do. All right, that's it for the day. Thank you guys. Tomorrow we will do the quiz, and then the back half of the class will be another. I'm going to come in with a printed sheet of questions that we can work on in groups or individually to kind of go through the first part of the class before we move on to the group test, the ratio test, and power series. All right, thanks for your work so far. See you guys.